this special conference. We all know that 1969 is a very special year that has marked mankind. That's when man walked on the moon. But that's not why we are here. We are here because of other very special and definitely marking event for all us, which was the launching of CECAM by Carl Moser, that time in Paris, with the idea of promoting research. And actually, if you look at what has happened since then, over these 50 years, we can agree that this was really a visionary move, because we moved from that initial situation or position of CECAM in Orsay to now a network of 17 nodes across Europe. And if you look, I mean, we embraced most of the relevant academic institutions are involved to the nodes, and I would say that most of the relevant research groups in Europe are definitely part of this institution in one way or another. And if you look at how we operate, we typically, in our flagship program, the core program of activities that we sustain every year, we organize around 80 activities per year, and we see around 2,000 scientists passing by through all of them, around half of them through Switzerland. So I think this is really a clear signal that this initial idea, this mission of promoting cooperation and fostering fundamental research among scientific communities to computationally intensive methods and grand challenges, and especially doing that by promoting international research and by bringing people together to work and advance into new and identify new challenges, is something that really was a need. And it's also quite amazing seeing that if you appreciate how much computational science has evolved since then, the fact that we still feel this sense of community around CECAM means that this was really a special idea, a vision that I hope will definitely continue in the future. So because of that, we are here to celebrate that and to do that in the way we like best, which is by discussing science, by talking about the research that we are doing, by learning from each other. And I hope that this will be really an engaging event that will be scientifically very encouraging and useful for all of us. When we decided how we were going to celebrate this special anniversary, we had a discussion. We finally decided that we were going to do this through a non-CECAM event. I am sure that all the organizers of events here in Lausanne, now for some years, when you have to organize it, I always, and Dominic before me, have this telco where we emphasize the importance of keeping a CECAM spirit, a workshop, not many people, being able to work together, ample time for discussions. And this is this is not really such a workshop. This is a conference where we are around 300 people. We have organized it in 8 plenary sessions and then a series of parallel ones, with the aim to bring really together as many possible people from our community and to, in a way, enlarge the type of interactions and among different areas. So I hope that by this singular event, we also keep the spirit through the conference. As you will have seen in the program, we will have a special event on Wednesday afternoon to what we have called the CECAM celebration. We will take advantage to deliver the Bernie Alder Prize. We'll have a roundtable with 7 outstanding panelists, especially to look into the challenges, because I think it's important now that we are at this 50, not so much looking back, we should celebrate, but we should look on the challenges that we have ahead of us as a community, and also for CECAM in terms of the roles it should play and how it can better serve and lead the community. So I hope this special event will be fruitful in that respect, and we will finish that with a celebration with a conference dinner at the Olympic Museum, which again, we will go in detail, but they will close the museum for us. We will have an aperitif. I think the weather is going to be good. Let's hope it stays like that so we can enjoy the whole setting. There is a possibility to visit for free the museum, and we'll have a dinner upstairs. I hope that will also be a good moment to celebrate what CECAM has represented for us and what should it keep on doing. So as I said, we have managed to bring together, I would say, the whole breadth of the different areas that characterize nowadays CECAM. And if you look at the different parallel sessions in the program, you see that really the areas that we cover is very broad. I've listed here from electronic structural physics principle modeling, also in material science, quantum and ab initio dynamics, more fundamental aspects of algorithm development, and also the very fastly developing topic of big data and high throughput and how to address that, and also sessions on statistical physics, physical chemistry, soft matter, and biophysics. So these are titles that have helped us to structure the program, but talks are a bit heterogeneous, and this is also done on purpose to facilitate that different people sit together in the room and that the discussions are lively and useful and interdisciplinary as normally CECAM meetings are. So before we move into the scientific program, a couple of more practical information. We will have, all the conference will stay on this stage, on this floor. So this is the plenary room. This is, and then we'll have the parallel ones that are at the two sides, so it's easy to move around. And I think that will also facilitate, we'll have also the coffee breaks, the lunch, everything will happen here. And I hope that also facilitates the exchange and communication among all of us. The plenaries and the Wednesday afternoon will be streamed. So if you have colleagues who haven't managed to make it but are interested in the talks, they can go through the CECAM50 webpage and follow us. And you will see that we have named the rooms according to CECAM history in a way. So we'll have here, Lausanne is the plenary, but then we have Blaricum. Blaricum is actually where, when an organization starts, it's always a bit difficult. There is always these mythical stories about what happened, and there is this meeting in the Netherlands where it is considered that that's where Carl kind of consolidated this idea before actually starting. So we thought that was really the very beginning, the prehistory, if you want. And then Orsay and Lyon have been the other places where CECAM has been located before coming here. So you will see the names, and then you can move around for the parallel talks. Because we are a big conference, we have these parallel talks, it's very important that you respect the allocated time for the talks, for the coffee breaks, and for the lunch. In the case of the parallel sessions, in order to keep the CECAM spirit, I've already emailed the speakers. Please, it's very important that you respect the time so that there is enough time for questions and discussions. Yeah? I know this is difficult, but please make an effort. And there are posters. There is no formal poster session because we are all together during all these days. The panels will be on, and then, again, it's a question that you try to meet each other and use the time that we are around to go through the posters. You will see that first we have a few posters explaining CECAM structure, the CECAM nodes, the project that we are running, ECAM, and so on. And then afterwards, you will have the posters from participants. Okay? And also, I will remind you this, but on Wednesday, after the plenary of the morning, we will have a group photo for the whole conference upstairs. We will guide you, but just start keeping that in mind. Something very important is that, as I said, this is a non-CECAM event. So this has been a challenge for CECAM team itself because we are a small team. We are used to other type of events. So we count with the help of some additional students, and everything is coordinated by Kiran. Kiran is here. So she's our current event coordinator. So anything serious, you can go to her. So all the members of the organizing committee can be easily identified because they are wearing this white T-shirt with the CECAM, and then in the back you have this clear symbol. This makes them an easy target please trade them with care, but you can easily identify. Obviously, I am a very easy target. I don't need to wear a T-shirt. And Sarah, the deputy director also. So anything associated to the organization, please come to any of us to address it, okay? Yeah, so something I wanted also to share with you, we have made today live because of the celebration. During the past months, we have taken advantage of people passing by Lausanne to grab them and ask them about what has been or what has CECAM meant to them. And actually now, if you go to I'm sure you at some point you have been in CECAM50, we added, if you haven't seen it, a special birthday message from Bernie Older, who unfortunately cannot make it here. But then on the bottom of the page, we have habilitated now this link, testimonials. If you click on it, here you can see the questions that we were asking to these people that were kind enough about what they value, what has been their experience at CECAM, and we have to edit them to have them in our repository properly done. But some of them have been kind enough to allow us to show or to share the unedited interviews. And I encourage you, you can go there. I will not run them. Some of them are here, but you can then click and see what they say. And if you feel like, and I think it would be nice to enhance the sampling, during the conference, in room I, which is at the right end of the stage, there is a room where during coffee breaks and lunch, you can go there and then also answer these 3 questions. Then we will ensemble everything, and then we will have it on our webpage. And I think it's if you listen to them, I think it's a good way to really understand what CECAM has meant during these years and how this is appreciated by the community. I think that's a good initiative, and I encourage you to take advantage to look at it. Actually, 1961, I learned that was also a very important year because one of our main entertainment gadgets was started. Actually, it was the first message was sent between 2 computers through the ARPANET. So it was really the beginning of the email. So I'm sure many of you have already found out, but you can be connected through the internet with EduRoam. In case you cannot and are very desperate, in the back of your registration then tells you how to connect through the local network. I only hope that looking at emails is not too distracting during the parallel sessions and during the talks here, but that allows you to be connected 24 hours. And a couple of final points. In the participant bag, there are a number of items that you have received. I wanted to point out 2. One is you have the program and the book of abstracts. As you know, with these conferences, there are always last-minute changes. So the very final version are accessible. I mean, the PDFs are uploaded in the CECAM50 webpage, so you can check there. In particular, I wanted to mention that this afternoon, we will have, in the first parallel session, there are 2 changes because Matthias Scheffler, unfortunately, last week let us know that he cannot make it. And then we were lucky enough that Luca Giringelli on short notice could replace him. And also Angel Rubio, because of a health problem, couldn't make it today, but he will come tomorrow. And then again, I'm very grateful to Hannes Johnson, who on short notice, he was even able to change his flight to be here in time. And then he will give the talk today. You should look at the name, at the title, because he says that he was even changing the title of the talk to give an even more interesting talk that he had planned initially. So hope this is definitely the case. And then Angel will replace Hansen tomorrow afternoon, okay? So I think these are the main changes. Some of the chair people, if you look into the program, has also changed, so be careful or double check who will be, if you're a speaker, in charge of your session. But, and finally, also, I wanted to mention that, I don't know if you have noticed, there is a special item in the back because we were in touch with a physicist who is now working on the history of science, and he has, Giovanni Battimelli, and he has been looking at the beginning, trying to understand how CECAM started, writing what is an early story of the early years of CECAM, looking through all the documents that we have. And I think this is the first written record of such a history. It doesn't cover the whole history of CECAM, but I think it can give you a flavor about how it started and the difficulties that this visionary idea had to consolidate as an institution in the French environment. So I'll finish here. Now we will really go to science. Thank you very much again for coming. And I'm hoping that this is really an exciting week for all of you. And then I now give the floor to Christophe Delago, who will be acting as a chairman for this first plenary session. So Christophe. Yeah.
Yes, so it's a pleasure to chair this first session, the first plenary session of this meeting. The speaker is Hardy Gross from the Max Planck Institute in Halle, and I should add that he's also former president of the CECAM Council. He will tell us about how to do non-adiabatic dynamics with exact factorization. Please, Hardy.
Yeah, thank you, Christophe. In fact, as of last week, my affiliation has changed from the Max Planck Institute to the Hebrew University. And in fact, it's the second talk I give with this new affiliation. Yeah, it's a great pleasure to be here to celebrate the 50th anniversary of CECAM. I think the first time I heard about CECAM was in the United States when I was a postdoc with Walter Cohn in Santa Barbara. And he at the time, this was in the 80s, when he had just established the Institute of Theoretical Physics, the ITP in Santa Barbara, that he mentioned several times to me that the way he designed the operation of the ITP was actually modeled after this wonderful institution that he knew in Paris, which was CECAM. So the ITP, or KITP as it's called today, is in fact an offspring of CECAM. Now, the first time I myself attended a CECAM workshop was when I was back in Europe in the early 90s. And I liked it so much that I kept coming back, and in the end I loved it, and I accepted some responsibilities, being a member of the council and then later on also president of the council for a number of years. Now, a quick glance at the program of this meeting shows the enormous scope that over the years CECAM has come to cover. So it's essentially static properties and dynamic properties of matter at all time and length scales. Now, in my talk today, I will focus on the smallest time and length scales, which is the realm that is governed by the time-dependent Schrödinger equation of electrons and nuclei. So this is a fancy title. One could also just say, no, it's not working anymore. Okay. So you could also just call it the dynamics of the coupled system of electrons and nuclei. Now, there is, if this is your goal, one simple case, the simplest case of all, which is the regime of ultra-fast processes, where ultra-fast means attoseconds up to maybe 5 femtoseconds or so. There, from the point of view of the electrons, the nuclei don't move, and it should be a very good approximation to clamp the nuclei at their, let's say, equilibrium position. Now, if we do that, then the remaining problem of many interacting electrons moving in a time-dependent external field is still an exponentially hard problem. So one way of dealing with it is to replace it by some kind of effective one-body problem. And one way of doing that is time-dependent density functional theory. So this is based on a theorem, a fundamental one-to-one correspondence between time-dependent potentials and the time-dependent density, which ultimately leads to an effective single particle problem. It's usually called time-dependent Kohn-Sham equations. They are written down here. So it's a single particle Schrödinger equation with an effective local potential, and this potential consists then of the static potential of the nuclei, Coulomb potential of clamped nuclei, an external field, let's say a laser field, and some terms, these two terms, time-dependent Hartree term and an exchange correlation term, that represent the interaction of the electrons with each other in an effective way. And the basic theorem that says that the density that follows from this single particle equation reproduces the density of the fully interacting system if you have a good approximation for this object here, the exchange correlation potential. Now I'm going to show you now such a calculation. It's for a system that consists of a buckyball, a porphyrin, and carotene. So this is a molecule, sometimes called triad molecule, that's being discussed for photovoltaic applications. So the idea is that this molecule is fixed to, let's say, a titanium dioxide surface. And then when you excite the system with light, then here you have an excitation, let's call it an exciton at the chromophore. And this then moves along the carotene, and when it hits a surface where this molecule is attached, the exciton will split, and in this way a photocurrent is produced. So it appears useful to do ab initio calculations to speed up, for example, this process, to find out under which conditions this can be as fast as possible and what the photo absorption cross-section is for a given molecule. So it's useful to do calculations, and I'm now going to show you such a time-dependent density functional calculation. Okay, so what you see here is starts this movie just after you have excited the system, and what you see is that nothing happens. So one was hoping that this excitation after the irradiation with light, that the exciton would move along the carotene, but you see it doesn't happen. Now this calculation is done with the approximation that I mentioned before, with clamped nuclei. And it's kind of the attitude of people coming from the electronic structure community, that, well, first step is always we clamp the nuclei and then do calculation for the electrons, and then we see later what the nuclei do. So here you see it's a disaster, right? What we want to describe doesn't happen. So if we do a better calculation where we allow the nuclei to move, then you see that very quickly there's some excitation going on in the whole molecule. And now have a closer look here at the buckyball. No, stop the movie. Sorry about that. Have a closer look at the buckyball. So it is now kind of purplish. I should mention what is shown here as a function of time is a density difference. So the time-dependent density minus the initial density. And what you see now is what originally was kind of purplish. is becoming more and more green here. Right, you see this very clearly. And this is a simulation for this finite system, indicating a charge oscillation on the scale of, here's the counters, 75 femtoseconds. This was predicted by this calculation and found later experimentally. So what is essential here is that without nuclear motion, you don't get the right answer. And the nuclei on that time scale move very, very little, right? You don't see it here with your eye, but they move. So I should mention this calculation was done by Carlo Andrea Rozzi and his group in Modena. Okay, now this is the motivation. So if we want to include nuclear motion in an honest way, we have to go back to the full problem, which is the Hamiltonian of the full electron nuclear system. That's written down here. So there's the kinetic energy of the nuclei, the nuclear Coulomb repulsion, kinetic energy of the electrons, electron-electron repulsion, and the electron-nuclear attraction. And with this Hamiltonian, in principle, we have to solve the time-dependent, the stationary Schrödinger equation, or if you have an external driving force, the time-dependent Schrödinger equation. So that sets the problem. Now, in the following, I will, just to set notation and to set the stage, repeat a few things that everybody knows. It's just to have a common starting point. So usually with this problem, one starts with what is known as Born-Oppenheimer approximation. In the previous Hamiltonian, one neglects the kinetic energy of the nuclei. And then the Hamiltonian that remains is this one, where the nuclear coordinates, denoted here as capital R, enter only as parameters. So the idea is then you fix the nuclear coordinates to a given set of vectors. For this given set of nuclear coordinates, you solve the many electron problem, and you do this for as many nuclear coordinates as you can, and this gives you then eigenvalues that depend on the nuclear coordinates as well as eigenfunctions, complete set of eigenfunctions at a given nuclear position. Now these eigenvalues as a function of R are the so-called Born-Oppenheimer or adiabatic potential energy surfaces, as shown in this cartoon. Okay, now there is a standard way of solving the full problem, and that's written down here. This is the so-called Born-Huang expansion. So you use the fact that for any given R, capital R, the Born-Oppenheimer states are complete set in the electronic Hilbert space. So you can expand with respect to the electronic coordinates in this complete set. But the slightly tricky aspect of it is that the full wave function depends also on the nuclear coordinates. So for any given nuclear coordinate, you expand in the complete set of Born-Oppenheimer states at that very same capital R. Which means that the expansion coefficients then will depend both on the nuclear coordinates and on time. So this is a formally exact representation of the full electron nuclear many-body wave function. If you plug this into the time-dependent Schrödinger equation and multiply from the left with Born-Oppenheimer states, you end up with this well-known coupled system for the coefficient functions chi of R and T. So this is what you see here. And what is evident is that you get as coupling between the different expansion coefficients, the so-called non-adiabatic coupling matrix elements of first order and second order. So you have gradient with respect to the nuclear coordinates acting here on the subscript of the Born-Oppenheimer states. Now, if we had only the first line, right? If we had only this, that's a nice Schrödinger equation, right? Just a nice thing. So if we could neglect these non-adiabatic coupling terms, then the problem would be very nice, right? It's just a Schrödinger equation and one nuclear wave packet moving forth and back in one potential energy surface. Right? That's what's indicated here. And then the corresponding approximation to the full electron-nuclear wave function is what's written down here, right? It's one single term of the Born-Huang expansion. The Born-Oppenheimer state at all capital R and this time-dependent nuclear wave packet. So this is what I call the adiabatic approximation, right? We neglect infinitely many contributions to the Born-Huang expansion. We keep only one term. That's the adiabatic approximation. And it's useful to remember that essentially all calculations of vibrational spectra, of phonons and so on, use this approximation. You just have one potential energy surface, and most of the time you do an additional approximation, which is known as the harmonic approximation, where you approximate, so you do a Taylor expansion, go to second order, so you approximate this by a parabola. And for the lowest lying states, this is a very good approximation usually. So normally, the calculation of vibrational spectra comes out extremely well within the adiabatic approximation, but not always. And the cases where it does not are depicted here. So when a situation is such that the lowest potential energy surface, like here, is very close with another surface, right? And that touches or comes close near the minimum of the first one, then obviously it's not enough to just deal with the lowest one. And then you have to face the full electron nuclear problem. You have to do the Born-Huang expansion, and there is demonstrated cases where the adiabatic approximation is just not enough. So the numbers are not right. But there are even more dramatic failures of the adiabatic approximation, which I'm going to show you now. There's two cases. One is famous Seville experiments, and the other is electronic currents that are associated with nuclear motion. So this is the first case. So here we assume that only two potential energy surfaces, Born-Oppenheimer surfaces, are important. And these two have an avoided crossing here. So this is the area where these non-adiabatic coupling matrix elements in the first equation of the Born-Huang expansion that I showed you become large. So if the lower surface, the red one, was not there, then we would just have this blue wave packet going forth and back, like in the adiabatic approximation. But then, since in this area here, at the avoided crossing, the non-adiabatic coupling terms are large, then there's a little contribution of this lower Born-Oppenheimer surface created, and this happens periodically whenever this wave packet goes across this avoided crossing. Right, so this is indicated here. This happens periodically, that a little contribution of the other surface is created. And in fact, since this is for a case where the asymptotic form of this lower surface corresponds to neutral, in this case sodium and iodine atoms, one can in fact measure them with pump probe spectroscopy, and when one can then very nicely read off here the periodicity of the oscillation that this wave packet here has. And if one then, like indicated here, starts at another place on the upper surface, then the periodicity will be different. So in this way we can map out the form of the upper surface, and for these beautiful experiments Ahmed Seville got the Nobel Prize in 1999. So everything is perfectly understood here, right? And there's no doubt the Born-Huang expansion is the right way to describe this problem. The only difficulty is that in practice we cannot do it normally for systems of interest. Think of this example that I showed you in the beginning, the triad molecule. No way of calculating the Born-Oppenheimer surfaces there. It's just too hard. You cannot do it. So that's one reason to think of other ways of dealing with the problem. So here another case, not so well known, which in a sense is an even more dramatic failure of the adiabatic approximation. And this deals with the electronic current density that is associated with nuclear motion. So think of a vibrational mode, right? So, but in the time domain. So nuclei just move slowly forth and back. Or think of an isomerization. So some simple motion on the lowest potential energy surface, let's say, of the nuclei. Now clearly, electrons in the adiabatic picture, they move with the nuclei, right? So there's an electronic current density, obviously, a local current density that kind of moves with the nuclei. So now let's try to calculate this electronic current density. And that's what's indicated here. So we make the adiabatic approximation, just a product of this time-dependent nuclear wave packet and one single Born-Oppenheimer state that represents that surface on which the nuclei move. If we then, from this wave function, calculate the electronic density just by taking the absolute square and integrating out the nuclear degrees of freedom, we get a very close, very good description of the time-dependent density. So now let's try the same with the current density. So we evaluate the expectation value of the current density operator with respect to this wave function. So that's written down here. Now you should remember this, let's say, the simplest case is a ground state Born-Oppenheimer surface, so the eigenstates, unless you have degeneracies, are real valued. This is what your quantum chemistry code gives you. And then, since the current density involves an imaginary part, you simply get 0 here. Right? So the current density associated with the adiabatic approximation is 0. Complete disaster. And it's not so easy to fix this problem. Right? While in the Ceval experiment, the situation is kind of easy. We have two surfaces and we just have to include the two to get the right answer. But here it turns out that typically you need many surfaces, many Born-Oppenheimer contributions to the Born-Wang series, hundreds, each of them very little, to give you the right answer for the current density. So it's a very hard problem. And the quantum chemistry community has tried all kinds of tricks to get a hold of this problem, and it's very hard. Okay, so this is the two, I would say, most dramatic failures. And as I said before, so the big difficulty is that the Born-Wang expansion for large systems and also solids is just not feasible. Now, you may think of ultimately treating the nuclear motion in one way or another with classical trajectories, but then thinking of a splitting of the nuclear wave packet like in the Ceval experiment, you immediately have a huge difficulty. Right? And this is what is the right classical force when the nuclear wave packet splits? Is it the gradient of the upper surface or is it the gradient of the lower surface? And things like Ehrenfest dynamics just give you an average force, which is totally unphysical. So this is a huge difficulty, and more or less out of desperation, the community invented algorithms like Tallier surface hopping, where you have a stochastic algorithm going forth and back between the surfaces. So for a certain time you have the gradient of the upper surface as the force, and then you hop, and for some time you have the gradient of the other surfaces, and so on. But there's no way of really deducing this in a proper way. Now, one thing that I will demonstrate through my talk is that this question, what the right classical force is when the nuclear wave packet splits, actually has a unique answer. There's no choices. Okay, so the way we have approached this problem, and this has been our hobby for the last 10 years maybe, is what we call the exact factorization. And this is a way of writing the full electron nuclear wave function as a single product of a nuclear wave function and an electronic wave function that depends parametrically on the nuclear coordinates. So it is a bit like the adiabatic approximation, except that this first factor is not a Born-Oppenheimer state. In particular, it's time dependent. So I will, in the following, demonstrate the consequences of this factorization. In particular, the equations of motion for each factor give rise to the concept of something like an exact geometric phase and unique time-dependent surfaces whose derivative then is the exact classical force on the nuclei, even when the nuclear wave packet splits. And after these more conceptual points, I will then show you two ways of exploiting these equations. One, we have termed it nuclear velocity perturbation theory, which once and for all solves this problem of calculating the electronic current density associated with nuclear motion. And finally, I will show you a new mixed quantum classical algorithm that gives you the right answer without surface hopping and without decoherence corrections. So since I will for sure run out of time in the end, I want to thank the people who have done all the work at this point. So adiabatic first produced these basic theorems of the exact factorization together with Nipa Maitra in New York, and this was really the starting point of everything. Then the mixed quantum classical algorithm was developed by Federica together with Seung-Kyu Min, Ivano Tavernelli. The static version of the factorization was first developed by Nikita Skidopoulos. This actually goes back almost 20 years when he was postdoc with me in Würzburg. And then various other aspects like the Berry phase were discussed by Ryan Request and Seung-Kyu Min. And the nuclear velocity perturbation theory, where the main topic, he was really the driving force, by Rodolphe Vieumier in Paris. So here's the first theorem. I should mention this factorization comes in two versions. There's a time-independent version and a time-dependent version, as you will see. And I want to start here with the time-independent version. So the theorem says that the full solution of the time-dependent Schrödinger, of the static Schrödinger equation, stationary Schrödinger equation, can be written in this factorized form, where the electronic factor, and this is a very important condition, has to be normalized to 1 for each fixed nuclear configuration. Now, if you look at this factorization, actually it's quite obvious that this has to be true. If you think of the absolute value of that equation, then on the left-hand side, absolute value of psi is the conditional, is the joint probability of finding electrons at little r and nuclei at capital R. And then we know from stochastics that any joint probability can be written as a product of a conditional probability times a marginal probability. And that's exactly the meaning of these two factors. So absolute square of this guy is the conditional probability of finding the electrons as little r given the nuclei are at capital R. And this is the probability of finding the nuclei at capital R. So in this form, it's kind of obvious that this has to be true. And in fact, remarks that this should be the case, you find it throughout the history of quantum mechanics. Recently, it was pointed out to me that the first person to mention this was in the 20s by John von Neumann. Then in the 70s, Jeffrey Hunter in Toronto has a couple of papers on this. So while this statement as such is kind of obvious, it wasn't really exploited in the sense before that what the consequences of this are, in particular what the equations of motion are for the two factors. So this, to the best of my knowledge, has not been looked at. Now, one immediate consequence is kind of obvious from the construction, is that the meaning of this nuclear factor is the absolute square, as I just said. If you plug it in here, is the diagonal of the nuclear n-body density matrix, right? This is the meaning. So nuclear n-body density matrix of the full system is taking the full wave function and integrating out the electronic degrees of freedom. If we then use the partial normalization condition for the electronic factor, we end up with chi squared. So that's the meaning of chi squared, basically by construction. And so in that sense, chi is a proper nuclear wave function. Now here are the two equations that govern the two factors. And let's start with the nuclear equation here. So that's a nice Schrödinger equation where a scalar potential appears, which, like in Born-Oppenheimer, is the eigenvalue of the other equation. And there's a vector potential. And this vector potential, is written down here, has the form of a so-called Berry connection. It's a nuclear gradient, so a gradient with respect to a nuclear coordinate that acts here on the subscript, and then the electronic degrees of freedom are integrated out. So this is a function of nuclear coordinates only, and in the equation it appears like a vector potential. So this is what we get. Now, this is reminiscent of the Born-Oppenheimer Berry connection and the corresponding Berry phase, but here these are not Born-Oppenheimer states, that's an important point, but they come from this more complicated equation. And this equation, as you see here, has the Born-Oppenheimer Hamiltonian in the beginning, and then two additional terms which are proportional to one of the nuclear mass. So you see immediately that in the infinite nuclear mass limit you're back to Born-Oppenheimer, as you should. Now let's have a look at these two terms here. The first thing you see is that here the nuclear wave function appears as well. Right? So you have to solve, if you want to solve these equations, you have to do it in a self-consistent way. Then, strangely, this vector potential appears also in the electronic equation, which is inconvenient because it makes this electronic equation a nonlinear equation in phi. Right? So phi is the eigenfunction here, but the vector potential itself, as you see here, depends on phi, so it's a nonlinear equation. Even worse, if you think of what these objects are here, right? This is a nuclear gradient acting on the electronic wave function. This is not even an operator in the electronic Hilbert space, right? This is something really weird. But if you think of expanding the eigenfunctions here in the Born-Oppenheimer basis, then you can actually evaluate this gradient with respect to nuclear coordinates. And you find that the resulting matrix is non-Hermitian. So this is, at first this was like a shock for me, but first of all it turns out that the eigenvalues are nevertheless real. So these guys are real, although this is a non-Hermitian operator. And it turns out that these terms, in the time-dependent version that you will see in a minute, are actually extremely important for the proper description of decoherence. So this is really what mediates the decoherence, these terms. Now, since this is a formally exact way of rewriting the full electronuclear Schrödinger equation, we call this the exact potential energy surface, these guys here, and this the exact Berry potential. So how do these guys look like? Well, first of all, to look at them, we need to have an exactly solvable model, and a simple model is the one by Shin and Matthew. Here we have two nuclei, this one and this one. They are fixed, they are clamped, and the third nucleus and one electron, they are allowed to move along the axis here. So this is 2 degrees of freedom. That's easy. You can solve it numerically exactly. And here are the Born-Oppenheimer potential energy surfaces for that problem. And these are the exact surfaces. So I switch forth and back a little bit here. You see that what is avoided crossings here, here and here, then become real crossings in the exact surfaces, so they are a bit like diabatic surfaces. What can we say about the Berry connection, the exact Berry connection? Well, here's the definition. Let's plug in the factorization here, in this place and in this place. Rewrite the nuclear wave function as absolute value times a phase. And then after 3 lines of algebra, we find this equation here, telling us that the vector potential, the Berry vector potential, is essentially the nuclear current density. So this expression here, in curly brackets, this is the exact nuclear current density evaluated from the full electron nuclear wave function by integrating out the electronic degrees of freedom. Right? And then dividing by the nuclear density. So this is really a velocity field. Right? And then there's a gauge-dependent term here. So this is the meaning of this vector potential. It's important to keep in mind. It's a velocity field. So here's this equation again. Right? The Berry potential is a velocity field minus gradient of the phase, and this is a gauge-dependent term. Okay. Now this equation can also be solved for the current density. Right? Same equation. Right? Just solve it for the current. Now in this form, it appears very familiar. This is what we learn in quantum mechanics 1. If we have a Schrödinger equation, like this one, with a vector potential and a scalar potential, we learn that the corresponding current density is this. But remember, this is not the way we calculated it. Like on the previous transparency, we started here from the true current density, the one that comes from the full electronuclear wave function. So what you have seen here in front of your eyes is a proof that this nuclear Schrödinger equation, this one here, not only gives you the true nuclear density, but also the true nuclear current density from this formula that you would get from the full electronuclear wave function. So this is something very unusual if you take a step back. Namely, usually when we have a system that consists of subsystems, right, then we need a density matrix to calculate properties exactly from one subsystem. Not here for the current density. We just need a Schrödinger equation. Right? Okay. Now, this exact vector potential defines something like an exact geometric phase. And then this raises the question, how does this exact geometric phase actually compare to the usual Born-Oppenheimer Berry phase, right? Where in the evaluation of the vector potential we have this Born-Oppenheimer states. And so just to mention, geometric phases are something very general, first discovered by Pancharatnam in the context of optics. They were investigated in detail by Michael Berry in the context of quantum mechanics. And whenever your basic Hamiltonian, like Born-Oppenheimer Hamiltonian, depends on a set of parameters, then you can evaluate from this equation that you saw before this so-called Berry phase. Now, you can do this in Born-Oppenheimer and for the exact vector potential. Now, to investigate how they differ, we look again at the Shin-Metyu model, but now in 2D. So the nucleus and the electron can move around in the plane. Right? So here's now the Born-Oppenheimer surfaces, and this has a proper conical intersection with Berry phase pi for this model. In fact, this point in configuration space corresponds to the equilateral triangle. So this is where at this nuclear configuration, this is where this conical intersection of Born-Oppenheimer surfaces appears. So that's this point here. Now, what is the true Berry phase? If you plug in the exact factorization electronic wave function, and it turns out it's 0. So at first this was really a shock. So you may know that there's really whole books of thousands of pages written on the Born-Oppenheimer Berry phase, and this kind of indicates that at least for this model, it's an artifact, right? It's an artifact associated with the Born-Oppenheimer approximation. So do we have to throw away all the books on the Berry phase? So I come back to this point in a second. Now, there's an interesting aspect of this, namely the fact that Born-Oppenheimer is the infinite nuclear mass limit of the exact formulation, right? So how can this be? If for finite nuclear mass you always get 0, but in Born-Oppenheimer, in the infinite nuclear mass limit, you get pi. How can this be? And we have investigated that in quite detail. I won't have the time to explain this, but it turns out that a certain property with respect to the nuclear coordinates, as you plot it as a function of nuclear mass, and this is these four plots here. This one is one particular nuclear mass, and then as you increase the nuclear mass, for all finite values, everything is smooth, and your Berry phase or your geometric phase is 0. But in the infinite nuclear mass limit, you say you have a discontinuity, right? These little arrows that you see here go up on the right-hand side, go down on the left-hand side, and it's this singular behavior that produces a Berry phase. So Born-Oppenheimer is actually a singular limit, right? Now, can one prove that this is always the case, that this Berry phase is always an artifact, let's say, of Born-Oppenheimer? And for a while we thought this is the case, but then we found an example where it's not so. So this is a certain nuclear mode that we look at here, which is a pseudo-rotation. And there it turns out that also the exact treatment gives you a finite value of the geometric phase. So if you just know Born-Oppenheimer, there's, so to say, two types of Born-Oppenheimer phases. One class that dies in the exact limit, and one class that survives in the exact limit. So I should emphasize here that what I call the exact Berry phase is actually not a Berry phase. So with the beautiful mathematical definition of Michael Berry, associated with the traditional Berry phase is this concept of infinitely slow motion, adiabatic transport, right? And perfectly well defined, everything beautiful, but it becomes difficult in the moment you want to make contact with experiment, right? Because real nuclei, they don't move infinitely slowly. They move the way they move. So once you want to make contact of the Born-Oppenheimer Berry phase with real experiments, then it gets difficult. So the point I want to emphasize here is what I showed you here as exact Berry phase. That's the real thing, right? There the nuclei move. So for this thing you have a chance to measure, while Born-Oppenheimer you won't be able to measure it. So now the time-dependent case. So here we have similar theorems. So we have a factorization of the time-dependent electron nuclear wave function as well. And we have then this partial normalization condition, and again the meaning of this object is that of a conditional probability amplitude. We have equations of motion that are somewhat reminiscent of the static case. So the nuclear equation is a nice Schrödinger equation with a vector potential and a scalar potential. And the electronic equation is complicated. We have this non-Hermitian term here. We have the vector potential appearing. So all complications that appear here. But in spite of the fact that this term is non-Hermitian, the norm as a function of time of this object is conserved. One can prove that. Now, since these equations, as I demonstrated before, give you the true nuclear density and the true nuclear current density, the gradient of the potential that appears there, of the time-dependent potential energy surface, that's the correct classical force. There's the freedom of a gauge transformation, but apart from that, that's it. So if you want ultimately to replace, let's say, the solution of the nuclear equation by some kind of classical trajectories, if you want these trajectories to reproduce the right current density and the right density, then there's no choices for the force. It's this one. So this is my claim. Now, how do these exact potential energy surfaces look like? And there we made a simple calculation again that models the Zeeweil experiment. So what you will see here is a series of snapshots. Just as a guide for the eye, I plot also the two lowest Born-Oppenheimer potential energy surfaces here. And so in blue you see the initial wave packet. Now you see a number of snapshots, and what is plotted in red are snapshots of the time-dependent potential energy surface. Right? So this object that appears in the nuclear Schrödinger equation. There's also these funny spikes here appearing. They should be ignored. They appear at places where the nuclear density is 10 to the minus 20. So they are just numerics. Just to be ignored. I'm just perfectly honest here. This is how it comes out of the computer. But they're not relevant. Okay, now what you see is that, as expected, the nuclear wave packet splits. Right? So typical Zeeweil experiment. And then what you see at the same time, the exact time-dependent potential energy surface develops a step. Now this step is reminiscent of surface hopping. We actually started 5 minutes late. Okay. It's reminiscent of surface hopping, but what you see here is actually not surface hopping. Right? It's just the time-dependent Schrödinger equation plotted in a somewhat unusual way. Okay, so when we have these two equations, the point to emphasize is that on the exact level, they are as good as the full time-dependent Schrödinger equation. So if you want to solve them exactly, that's not really an advantage. Also numerically, it's not an advantage. But the crucial thing is that you have two separate equations here for electrons and nuclei, so you can actually apply different kinds of approximations to the two systems. For example, you can approximate the nuclear time-dependent Schrödinger equation with a set of classical Newton equations, so a swarm of trajectories. And as I emphasized, there's no choices for the force. It's the gradient of this time-dependent surface. Now this surface comes from the electronic equation, which is still a correlated many electron problem, so that's hard. So one way of dealing with that is to density functionalize this equation. It's not a trivial thing to do because it's not really a proper Schrödinger equation, but one can prove that it's possible. And then one propagates that. I'm going to show you such a result here, which is again for the Shin-Metyu model. So you nicely reproduce the populations here on the different potential energy surfaces that I showed you for the Shin-Metyu model before. But what is most exciting is that without any additional effort, without surface hopping, without doing anything in addition, we get a very good description of decoherence. So what is plotted here as a function of time on the lower plot is a measure of decoherence, so it's essentially the off-diagonal of the electronic one body of the electronic density matrix with respect to the Born-Oppenheimer basis. And you see in green is the exact result, with reddish dots is this algorithm, this mixed quantum classical algorithm that I mentioned, and in Ehrenfest and likewise surface hopping, you don't get decoherence. Right? So this is a crucial finding, that without any special effort, these equations give you the right thing. And in fact, they can be applied to real-world systems, and this is a calculation for the oxyrain molecule. So this is within a certain laser pulse. You have a ring opening of this molecule, and there's two competing mechanisms. Either the oxygen here moves to one of the carbons, as you see here, or as you see here, or you have a carbon-carbon stretch. And so you can really do a calculation for this kind of molecule, and the prediction then is that the ring opening by the motion of oxygen to the carbon is about 4 times more probable than the carbon-carbon stretch. And again, this is a similar plot to before. If you look at specifically at decoherence, this is not well described in surface hopping. That's this plot here. While our algorithm gives a similar result in this case as a surface hopping plus decoherence correction. So this is one message. I also should say this algorithm is implemented in CPMD, so anyone can use it. And the final remark, how we deal with this big problem of calculating electronic current densities that are associated with nuclear motion. Here we just we look at the electronic equation and just treat these terms that are proportional to 1 over m, to 1 over the nuclear mass. We treat them in perturbation theory. And the nice thing of this equation is really that you have a small parameter, right? This is 1 of the nuclear mass. And here you treat all non-adiabatic effects at once with these red terms. So the many-body people know about Migdal theorem, right? And in fact, one can see that the electron-phonon interaction is part of this, right? But it's not. These red terms here are not only electron-phonon interaction; they are much more. They're all non-adiabatic effects, and you can treat them in perturbation theory. And this comes out marvelously. So this difficulty of calculating electronic current densities, which we did for a model here, comes out very nicely. So that's for a model that I don't have the time to explain. You see here the current density associated with a nuclear isomerization. So this would be the object that in adiabatic approximation would be vanishing identically. And with this nuclear velocity perturbation theory, you get a very good account of the exact result. And this can in fact be exploited for real-world problems in the calculation of vibrational circular dichroism, which I will not show you the details. Here's the relevant numbers that you can calculate, and they come out in good agreement with other methods that are much harder and less accurate, I would say. So here's a summary of the exact factorization. So first is this factorized form of the full electron nuclear wave function, and this defines something like an exact Berry phase and a time-dependent potential energy surface that has these natural smooth jumps between Born-Oppenheimer states. And this gives rise to a mixed quantum classical algorithm. The electronic equation can be density functionalized, And finally, this is something that I didn't mention, one can also apply this factorization to electrons only. For example, you factor out one electron from the rest, and you can look at the equations of motion, which then give you something like a concept of an exact single active electron potential, which has been much used in the strong laser community. So this is my last transparency. The take-home message is that the exact factorization on one hand is useful to settle conceptual issues, like you can define a unique classical force on the nuclei even when the nuclear wave packet splits, and you can define, without recourse to the Born-Oppenheim approximation, an exact geometric phase. So this is more conceptual issues, but it's also useful to develop practical algorithms. This mixed quantum classical algorithm was one example where you don't need surface hopping and decoherence. You get it for free. And the nuclear velocity perturbation theory that allows you to calculate vibrational dichroism and electronic flux densities. Thank you for your attention.
Thank you, Hardy, for this wonderful lecture. This is very much against the CECAM spirit, but there is time only for one question, if at all. And please use the, yes, Julia, please, but wait for the microphone, please, because we need it for the recording. It's coming.
Can your the formalism that you have presented be used or generalized to compute photoluminescence spectra?
I'm sure it can. In fact, we are currently working on a linear response version of all this. So yes, it's a good project, yes. Yes, but we haven't done it yet. But we are on the way.
But so you're saying we should, it's a good thing to think about.
Yeah, absolutely. Yep.
Okay, in the interest of time, let's conclude here and let's thank Hardy again.